So the following session is called Protocol Correctness Validation in the OVS OVN Test Suites, and it's a presentation by Ihar from Red Hat. Enjoy.
I'm Ihar from Red Hat, and in this short talk, I will briefly walk you through the why and the how of testing protocol correctness in our test suites. We will start by defining what I mean when saying protocol validation, then give some reasons on why it should be part of your testing approach, and finally, which is probably the more interesting and practical part for you, we'll look at a number of tools that are available in test suite frameworks to help with the goal. Now, what do I mean when saying protocol validation? Throughout this talk, all I mean by that is as simple as make sure that software produces on-the-wire packets that conform to the corresponding RFC. In essence, the goal would be to test that observed test packets match idealized predefined formats. Let's say we'd like to test a new feature in OVN. Testing usually goes as follows. Assuming the feature has its own API, we validate that the API creates expected northbound objects. Then we may also validate that these northbound objects are converted to southbound properly. Perhaps we may also then validate that OVN controller translates these southbound objects into corresponding open flow table rules. Sometimes we stop right there. But does the feature work? Unless we send some packets through the wire and validate they went through as expected, we don't really know. Maybe new open flow rules have a mistake. Maybe older rules affect the behavior of new rules. Maybe there's a bug somewhere in data path. Whatever it is, unless we validate packets on the wire, we don't really know. What can we do to test deeper? We could use tracing tools like OVN trace. It can show which path OVN believes the packet will take, yet it's only a simulation of the intention. We still don't send a single packet on the wire, and of course we can't receive any expected replies to it. But why would we even care? I'd like to make a controversial claim that end-to-end testing should be part of every project. At least that includes underlying components of the whole system. Additionally, network problems are happening in flight when instrumentation is not always enabled. These issues are hard to debug. You have to use different tools, and so it's complex. And it would make sense to invest some time into protocol validation and not spend hours in the field. Also, it just feels good to be correct. So what do we want? So what we want is first prepare a packet, then inject it into the data plane, then receive it on the other end if that's expected, perhaps also receive the corresponding reply from peers of the protocol, and finally confirm that observed packets match what's expected. How do we do it? First of all, basics. In test environment, we have an appctl receive command that accepts an OVS port and a hex string with packet payload. There's 1 byte represented by 2 hex characters. When this command is executed, the packet is actually injected into the data path, and we can observe how the pipeline handles it. Next question is how to define the packet to be injected. Those among us who think in binary can easily produce the string, no tools needed, and just put the necessary payload into a shell string, checksums recalculated as needed, then pass the result to the receive command. Very easy. Sadly, the rest of us who are not as smart and we may need some helper tools. And actually, there are already some helpers readily available in the test suites, so let's walk through some of them. First, something specific to OVN controller. There is a special inject packet appctl command available for the controller process. You can define a packet in southbound logical flow form that's similar to OpenFlow format, including the import, then call the inject packet command. The command will make the controller to transform the packet definition into an actual payload and inject it using the configured import. There are some caveats. First of all, it's OVN controller specific. Also, the implementation is limited and doesn't allow to store more than a single pending packet in the queue. On each controller main loop, the pending packet is processed, freeing the slot for the next packet. If the system is slow and we inject packets in quick succession and the main loop of the controller can't keep up, then only the first packet may be injected. Finally, the input is in logical flow format with its own limitations. So forget about constructing DNS packets, let's say. A variation to this tool that is not OVN specific is OVS OFCTL compose packet command. This command receives an open flow definition, which is, by the way, not identical to OVN logical flows, and returns the packet payload as a hex string. Note the --bear argument passed to the command below. Without it, the command returns a string that cannot be directly passed to receive command. Also note that this command only produces the payload string, so you have to inject it yourself. Now let's say you want not only to inject a packet into the data path, but also confirm it is received by the output port. For this, you may configure the output port to capture in pcap file using tx pcap option. And then you'd inject the packet through the input port, and finally you would use OVS pcap tool to convert collected pcap data into text format and compare the result with the expected packet definition. Let's look at what you can do with compose packet command. Let's say you'd like to validate that NAT is working when the packet traverses a router. First, you compose the source packet using internal IP address. You expect the packet on the output port to have a different external IP address. That's why it's NAT. Since the source flow definition is just a symbolic presentation of the packet payload and not a hex string, you can easily apply a simple set rule to the definition, replacing any occurrence of the source IP address with the expected final one. You also produce the expected payload from the result. Finally, you inject your packet through the input port. Dump the observed packets on the output port and compare the result with expected packet. Note that in the example above, the checksum of the final packet with the new IP address would change. But it doesn't matter, compose packet correctly recalculates it. This happened automatically for us. We haven't encoded a single payload field in binary. Side note, the command may be expanded to accommodate to special test needs. For example, a --bat checksum option was added recently to accommodate for a test that validated checksum behavior. If your use case is not supported by the tool, perhaps it can be extended to accommodate. The final tool that I would like to cover in this talk is format packet. The tool is built around the well-known Scapy library that supports different, even obscure protocols. This tool is available in OVN test suite and is meant to be used where compose packet and similar tools are not enough. Let's take a look at an example. In the first section of the test code snippet, we define the packet format. This format uses Scapy as the backend. The string is just a piece of Python code using Scapy classes. Here you can see that a DHCP version 6 packet with an additional client ID option is defined. In the second line, format packet helper function is called to produce the hex string for the packet payload, and the result of the function is passed to receive command. As I said, the actual packet definition format is just a Python code that uses Scapy-specific classes to chain the protocol headers. For more info on what's supported, please consult Scapy documentation or just start Python REPL, import Scapy modules into the environment, and start playing with it like with any other Python code. When I say the helper is Scapy based, I really mean it. The first implementation of the helper was as simple as what you see above. Here, the function constructs a short Python string that effectively executes the passed argument as Python code, see the raw call there, then prints out the string result for the Scapy packet. Each call runs in a separate Python interpreter. Obviously, starting a Python interpreter to construct a single packet payload may be wasteful when you need to do it tens of times in the same test case. So the second implementation of the tool instead built a simple Unix control daemon around the same concept. The server would start once per test case and only when it's actually needed. With this version, we should be able to adopt the helper in more of test scenarios. There are some limitations to be aware of. First, Unix control servers have a maximum number of simultaneous clients that they can serve, and since each format packet call is a separate client, it may be not wise to run too many of the calls in parallel. This should not be a problem for test cases in general, but some may want to run packet generation and injection in multiple threads. Another thing to note is, yes, the tool uses Scapy, which is very powerful and supports lots of more obscure protocols, but it's not almighty. While the majority of your needs should be covered by the library, you may still find some gaps. Thankfully, input to the helper is Python code, so you can use other Python modules from standard library if needed. Finally, I'd like to point out that Unix control communication in Python necessarily slows down the helper. While technically it would work for any packet construction, it's better to stick to other tools if you don't have to use Scapy. Since compose packet is based on OpenFlow rules, I'd suggest to use format packet for more complex use cases, usually for higher network layers. But regardless of what you decide to use, please let's try to avoid coding any more payloads in test cases in binary. We don't write tests in machine code, and we should not do the same for network data. That's all I had for this talk. I hope this was at least somewhat helpful. If you have any feedback on the tools I mentioned, perhaps a use case is not covered by some of them, please let me know and we can think of which tools could be extended to cover it. Thanks for your attention.
All right. Thank you very much, Ihar, for your presentation. So let's see. There is one question from Aaron on your presentation, and he says, any plans to go back and modify existing test cases?
Hey, first of all, yes, it's on my agenda, but also it was very nice to see that some other contributors already picked up the tool. And just very recently, there was a series from Mark modifying a bunch of existing tests, more complex ones, to use a format packet. I think compose packet is not as yet adopted, so we are going to look at that. Some of the tests that are currently using format packet may actually use compose packet instead, and so we should also look at transferring those easier cases to OVS tools.
All right, thanks for answering that question. I see no further questions at the moment, so I think we're good to go to the next session. Thanks a lot, Ihar, for your presentation. And I think it will be good for people to take this on and update their test.